So why are LLMs so expensive? At Arena, we see this a lot because we're serving LLMs to millions of people, and we get to see very much in the real world how much these agentic sessions really cost, and it is very, very high. And so today we'll explain a little bit on why it's so high and also how we end up calculating a reasonable heuristic for cost per task for our Pareto graphs on our leaderboard. All right. So if you've ever been to a model API documentation, you'll probably see something, a cost table that says something like in, out, and cache. And we'll just talk about this just briefly. So in is usually cheaper than out, and cache is the cheapest of all. So in will be like $1, out will be $10, and cache will be like a cent. So what do these things actually mean if you're not familiar? In is the cost usually per million input tokens to the model. So the model takes in a bunch of text. Out is the dollar per output token the model produces. This includes reasoning and also any texted outputs that you look at. And caching is something special where when our prefix is identical to a previous input we had, we can get that input for a lot cheaper. So roughly, if you do some input, let's say this is my first conversation with the LLM. It started from empty context. My first prompt will go in like this. And that will not be cached, so that'd be charged at $1 per million. And then I'll have some output that comes from there. That will probably be shorter. Actually, it depends. It depends if there's like lots of reasoning. So actually, let's say there is reasoning. There's like, my prompt is like 1,000 tokens. I might have a, let's say, something reasonable. Let's just say it's not to scale. I'll have a bunch of reasoning tokens, and then I'll have my final output tokens, which is whatever like markdown lines that I'm consuming as a person, and that's my first turn. And if you look at the first turn, it's going to be super cheap. I mean, it's like charged per million. Like you'll probably see this, it'll be like a couple cents. Say, wow, AI is so cheap. Why does anything cost any money at all? Now, what happens is on this next turn, we can hope to have a cache hit. So usually, I think it depends on the provider, but usually only the previous prompt gets cache hit. And so like this will be a cache hit. And you'll be submitting, of course, the previous outputs become part of the new prompt, right? So all of this that I previously said will be part of a new prompt. And then I'll have my actual new like user request here, okay? And I'll be paying normal input prices for all of these. So these will be charged at $1 per million. And this will be charged at, because it's a shared prefix with this previous one, right? These are equal. This will be charged at cent per million. And then my output, of course, will be charged at the output price. So a little bit of reasoning and a little bit of output, right? Okay, cool. So this just got a little bit more expensive. But we got saved by this caching component here. And you can see, right, if we do our next turn, would be this. You can see how this is building up into a triangle. You can see how I'm starting to build this triangle, and it'll keep going for all eternity, longer and longer. With like, these parts over here, you kind of get the picture. Okay, so what's happening here? I'm being charged roughly for not only what I got this turn, but repassing in what I got last turn back into the conversation. Now, luckily, I have caching, so when I pass things back in, they are roughly, usually about 10% of the price. So that's the saving grace here. Now, this is per back and forth. So in classical chat use cases, this was just I say something, the LLM says something, I say something again, and that's the back and forth. That's the transition between each one of these lines. Now, in agentic AI, it's different because it's not always me talking to the model. Sometimes it's a model talking to the files on my computer, checking the web, whatever. And all of those is also a back and forth. And in fact, the back and forth frequency of the model to the environment is much higher with agentic AI than it is with model to human. And so you end up with these tons of back and forth. Now, every time you go back and forth, you're moving off of the GPU into your local to like call a command and wait for the response. And then, which of course is lots of latency, comes back, and then you have to reload that sequence in. And so you get a lot of these lines, a lot of little ones, right? Even if this is like infinitesimally small, a one token input, I still have to pay for this entire chunk right here all over again. And so even if my tool calls are small, let's say they only return exit code 0 or 1, I still have to pay that initial context over and over and over again. And that's not too bad when you have a cache hit. When you have tool calls, usually it's very quick, so you're hitting cache every time. It shouldn't be too much money. Again, it'll grow at 1/10 of the price. But if you have a cache miss, then you're screwed. So what is a cache miss? Let's say I've had this conversation, it's going on for a long time, and let's say my conversation, I've been talking back and forth for a straight up hour, and it's reached 1 million tokens in length, a whole million tokens. And then I just walk away, because I have to eat dinner or something. Come back and I say hi. And you would think hi doesn't cost a lot of money. However, you're paying for the entire context. And so in that case, this is where you get completely screwed. And you'll have, this is 1 million, so this will literally cost you $1 to say hi, plus whatever tiny little outcome. Let's say the model says hi back really quickly. You have a little tiny thing here that's negligible. But now you've paid an entire dollar for hi. So that's what happens when you miss cache. So one of the most important things is to never miss cache. But in practice, it happens because humans aren't here 24 hours a day to talk to AI all day. Okay, so roughly that's a picture of caching and why it's important. I think it's time to move on to a different area. Yeah, I'm going to talk about a couple strategies for saving costs. So kind of briefly, if we model what this is really, it's like this growing triangle. This growing triangle of costs where, each one of these things is a back and forth to the model. Now, this is charged by, you can see the cost grows by the square. Even if I'm caching, it doesn't matter. It still grows by the square. It's not very efficient. One thing is you want context management. This is where compaction comes in. People are probably somewhat familiar with that. But what happens is, instead of having a triangle like this, maybe I can just draw over it. I'm going to have a context that grows like this, and then I'll contract it because I've compacted my cache, let's say, by 90%. And then it'll grow like this again. And then this will save costs. I guess I should have done something. Sorry, this is a little gross. It's just like this, right? So this will save me a lot of money. And for this reason, you might see the default compaction threshold in apps like Claude Code or Codex is not the 1 million context that the models advertise. It's probably around 200 to 300K because it's simply way too expensive to be running models all the way to 1 million and back and 1 million and back and 1 million and back. Okay, so that's a picture of how compaction changes your cost profile. It causes shrinkages where you do compaction, so that's efficient. Now let's look at kind of a broader view of the cost of a single session. So let's say, I'm going to think how to draw this perfectly here. We're going to roughly have a graph, and maybe I'll show a real one of these once I'm done, but I'm going to show you an example. So this is turns, and then this is, not the cumulative cost, but merely the cost of a single turn. And what you'll see, and I'll draw a couple things here. I'll put a dotted line here for a compaction that happens in the future. And then I will mark misses, cache misses with blue. and then cache hits with pink. And for this purpose, I think output tokens won't be enough of a, in the long run, enough of a cost issue that I'll just ignore it. So what you end up with is, if you look at something like this, the initial turns will be very cheap because our context is small. So we'll have little turns. It'll be like this. Okay. It's growing, but it's not too bad. Actually, no, this is not too bad because the first turn will be small and we're cache hitting, mostly cache hitting, except for the new context, of course. But say that we stop here. And so I walk away for more than like an hour or something and I come back, it's a miss. Well, that miss is going to be super expensive. It's going to be way high. And then I'll go back to hitting. Okay, so it'll be like this, let's say miss again, boom, another miss, right? It's going to be really high. And then keep going, and then I hit a compaction threshold. This brings everything back down, and I'm, I guess, to be pedantic, this will be a miss. So it'll be like this, and then like this. And we're growing again. All right, so the conclusion here is a couple different things. So again, this is the cost per interaction. Every time it's blue is a miss, and it costs way more than the rest of my interactions combined. And then the pink here is when I do hit my cache, which you can see is growing with each, it's growing with each interaction, right? Because it's cumulative of all the past interactions. But it's nothing compared to the miss. And in the long run, my cost might be dominated by these giant misses. You'll see how compaction lowers the cost for everybody. That's a great thing. Everybody loves compaction. Cool. Okay. So how do we estimate cost at Arena? It's clear that input-output is one component, of course, that tells us the rate in which our session will grow in cost. But the dominating factor is this context growth and how we keep repaying for it, if we hit cache or not, if we compact or not. So all of this is dependent on how the user and model behave together and not necessarily how in and out costs. So I have to erase because I want to draw here. I wanted to draw this idea of tasks. So inside an agentic session, on agent mode, we actually break things down into tasks, which is a larger unit than turns. So what is a task? Say I'm asking to update my personal website. That's one task. And then afterwards, I ask it to update my resume. That's a new task, all in the same session, context carried over between, but those are different tasks. So let's mark tasks on the bottom here. So this is task 1, and then task 2, task 3, and then we're going to go all the way to task n. And what we'll see, remember, there's triangles everywhere. So there's a triangle for the cost of task 1, and this is assume no compactions for a second here. Okay, so but what happens after that is when I do task 2, I carry over all the context from task 1. So this is the growth of the context. So I have to carry over all of this. Granted, this will be a cache hit, but regardless, I'm carrying over a lot. And then there'll be some cost of the additive cost of new tokens to accomplish my new task. And then so on and so forth. I'll have a new triangle here. Of course, none of this is to scale. And then somewhere along here, I'll have some triangle and then some very long, some very long bar. And what you'll see, right, is in the long run, and not drawn here, but really like if you're going to draw it to scale in the long run, many tasks on the line, let's say 100 tasks, just a little tiny triangle, and a massive carryover context, where the dominating cost is actually just this context, which is also why you want to compact. If you compact, you make this smaller. Okay, so what does that mean for estimating a model's cost? It feels a little weird to be using this entire triangle. Why is that? Because different models have different levels of retention. In fact, better models will be more retentive. People will want to go back to sessions with stronger models because that model is good. It can solve their previous task. So they figure, hey, it'll solve task n+1. Therefore, I'll go back to the session to solve the task. And so what you'll see, actually, before I go into that, a kind of obvious degenerate scenario is a model that is completely worthless. Well, a model that's completely worthless, no matter how cheap, I'll never use. Therefore, it'll cost 0. It's kind of like this. Say a user using a terrible model attempts to do task 1 and then abandons the session because it's clear it cannot solve task 1, so it's done. It's never gonna consume these. And so we don't want a cost counting scheme that ends up penalizing this regime too much, because we don't want to say good models are extremely expensive just because they're worth using. Doesn't really make sense. So there's 2 ways. One way is that you just count the cost to do a task. So I could just sum up these pink triangles here and say, hey, given basically, what's the added cost of going from task I to I plus 1, not counting the carryover context cost. It's a very reasonable way, and it's grounded because it represents essentially cost per reasonable unit of work. If we just look at turns, for example, that's also too granular because a really bad model might take many, many turns to solve a task. So let's say Fable solves a task in 2 turns, and a really weak model solves a task in 10 turns. So it could be the case that that really cheap model is more expensive than Fable because Fable just got it done like that. And so that's why we can't just look at a per turn cost, because it might take more turns to get where you're going. And so that's why we look at task-based costs. Now, in practice, calculating this is kind of a pain in the butt. And so what we end up doing is we end up looking as a heuristic just at these literally at these first 2 or 3 tasks before the context starts dominating. And so there'll be a little bit of effect of models being more attractive and therefore having a couple more tasks. But in general, we're not going to be counting this scenario where most of what we're looking at is just carryover context because this model is so retentive. Cool. So that's how we're going to look at costs in Arena for agent mode. Again, in summary, there's a couple things we want to look out for. Carryover context, which as we've seen, dominates the cost equation in the long run. So strong models will have more carryover context because they're more retentive and therefore look more expensive even though they're not. And on the other hand, just looking at a per turn or even per token cost, you're not going to see the kind of turn efficiency of the model. Again, turns are what actually costs money. And so a cheap model that requires many turns will also be extremely expensive. And therefore, we just look at the individual cost across an entire task, whether that takes 10 turns to solve the task or 100. So I've collected a graph here. It's roughly showing all the turns on the bottom and the cost for that exact turn. You'll see spikes. Spikes are, as we've seen before, the catch misses. So a user walked away, came back later, and we incur a very high cost when the user comes back. In fact, I think a lot of work is to avoid this return cost, whether it is preemptively compacting a session to make it smaller before they return, or holding out a cache for longer if that's possible, if you suspect the user would return. These are valid strategies to try to mitigate the cost, depending on what you have control over. And also you can see that when there's a compaction, suddenly all the costs immediately drop. So each turn becomes much cheaper because we're not carrying over the baggage from previous contexts this entire time. And so all in all, you can see that these sessions are super expensive. At the end of the day, they're really expensive, and it's because of this squaring. I want to back up and let some of you know who might not be familiar why the costs are even charged this way. Like, why is everything going up by the square? The answer is because these models are stateless. And so they require all previous contexts to be passed in at all times. And in fact, the model itself, bearing linear attention techniques and stuff, like a very traditional transformer, is not compressing that whatsoever in their state. And so they literally have to do more and more computation as the context gets longer. That's a good thing, because as context gets longer, then you might need more computation in order to produce your next output. So that's kind of why transformers are nice. But that also means that it costs more and more and more for a long context length. At minimum, your activations, will grow much larger. So that kind of yields two things. One is it like literally costs more compute to do this. Every time you talk and your conversation gets longer, the amount of computation needed to be done on hardware's consuming power goes up. The second piece is this is why caching exists, because if they have that prefix of your conversation preloaded into the GPU or stored somewhere where the activations can be loaded into the GPU quickly, we avoid recomputing everything. So when you come back, they literally have to prefill the entire sequence, let's say 1 million tokens of computation. That's really slow. If they already stored that in the state, then they can start producing the next token much faster because they don't have to recompute every single activation. It's already stored. They can reuse most of it. And so when you do a cache hit, it's much cheaper for you because it's also much cheaper for the inference provider who doesn't have to do as much computation. Of course, there's some storage fee. Needing to keep your activation around just costs money. And so that's why sometimes, for example, on the Anthropic for the Anthropic caching, you pay a little extra to guarantee that your cache stays around, because that means you have to keep it around. And so that ends up being why these things are priced in this way. And when you look closer at like transformer architecture, how serving works, then it becomes clear why these things are so expensive. And so when you use Arena and use a long agent session, it gets long, you come back later, you go eat dinner, then you come back. All of this is really, really expensive because you're passing in everything back in. And if it's a strong model like Fable that's very big and very expensive, it could cost hundreds of dollars, if not more, for a single session, just because there's so much back and forth between tool calls and the model and the user and the model, and some tool calls take a long time and some users take a long time to come back. And at the end of the day, it wouldn't be unreasonable to see $1,000 session. And that is expensive. There's also like small behaviors that change how much a model costs. So you might think that just like the biggest model is the most expensive, like, oh, Fable will just be the most expensive because it's the biggest model in the stack. That's not necessarily true. All things equal, that would be true. However, there's a couple things helping Fable may be able to solve tasks faster with less steps. And like you said, each step is adding a line to that triangle that we drew earlier. And so if Fable can solve it in 2 steps and another model can solve it in 10 steps, Fable might actually be cheaper, even though per unit, per token, it's much more expensive. Sometimes it's like, there's models will think more. So you might see like Opus Max might think a lot more than Opus Medium, but that comes at, not a linear return. So it's not like, if I pay an extra $1 thinking, I get like $1 more value. It might be I get like 10 cents more value. On like a Pareto graph, you'll see like these really expensive models, but they don't gain that much over their like medium alternatives, because most tasks maybe can be solved without using like max thinking, for example. Right now, like Opus Max might be our most expensive model, just because it's thinking so much. If the thinking is passed back, or like if the model makes more steps or produces more output tokens, whether that's like extra tool calls or extra thinking, you actually incur that cost over and over again, right? Because you have to feed this back in every single time. Some models don't feed reasoning back in, but I think most end up doing now. So you're feeding this in context back in. So not only did you pay more for output on turn I, you have to repay that as input over and over again for all sessions until you compact. And so that's an example of how maybe a small change, like let's say you just double how long you think, you end up repaying that over and over and over again as we build out the triangle that we drew. So in that saying, something like a max model might be actually like much more expensive than a higher medium version of itself, just because you're repaying everything over and over. To be specific, our calculation looks at a couple of things. We look at cost per task, estimated by looking at the first 3 tasks in a session, and all their costs are like real life calculated. So we're taking the pricing from the API page, what you would get if you use the model, and including cache hit or miss. So if it misses, it'll cost more money. And this is just real world usage. So misses are just like how you would see in the real world. Say if you were using agents in the wild for your work or something, you will miss, it's inevitable. And so yeah, we're calculating with everything included, with compaction thresholds and cache misses and cache hits and more tool calls, less tool calls, all of that together to get an exact kind of real world estimate of what these models cost per task. We have a 7-day estimation window. So we don't want to use cost estimates that are too stale. Why? Because our own harness is changing, and the harness controls things sometimes like compaction, which, as you saw, is a huge impact on how much a session costs. So if we changed our compaction threshold, which right now is quite high, we might lower it. Then if we lowered it, then suddenly all the models would seem cheaper. So, and they wouldn't really be, just because we changed something on our harness side. And it would be a little bit, it would be weird to keep using cost estimates from, a month before we made this change today, because it simply isn't true anymore. And so that's why we have actually a pretty short, like 14 7-day window on which sessions we use to estimate cost. It's also why we look at like the first 3 task heuristic, because it kind of avoids these weird longer context things that end up affecting things beyond just the model kind of cost to do a task itself.